Welcome back. Let me continue. Just now I said that, let's say this is a fixed cylinder and it is attached to the string and connected to this one, the mesh, let's say. And as a result, there's a final movement of acceleration A downward due to the gravity. And for this question, we try to analyze. So two things that you need to involve. One is the Newton's second law for the force, and second is the Newton's second law for the torque. Angular force, sometimes for the protein increase. So the first thing is for this object, let me put it as A. This is object B. So for object A, we know that sigma F equal to ma, and the A is downward, and I consider down is positive. Therefore, mg minus T equal ma, and T is what? mg minus ma, or mg minus A. On the other hand, we also know that sigma tau equal I alpha. This I is a I cylinder. I is actually, for this case, is actually half mr squared. And later I will cover what is the I, but at this moment we just leave it first. Then we continue. If a sigma tau equal to I alpha, then we can say that this one, the tau is always force times displacement. So it's actually TR equal to I alpha. And since we know that what is T, mg minus A R equal to half mr squared alpha. Bear in mind, the m here is the mass of the cylinder, and the m here is the mass of the block. So you can see there's a relationship between each other, and this is something about it. How do you discuss, how do you analyze the question? And the one involved Newton's second law. And maybe I can give you some introduction and also some revision on the tau. And for the tau, the definition is, in general, is RF sine theta, in general. But somehow, it is better we put it that is R F perpendicular times R. What is the meaning of this one? Which means that we try to find out the component of R that is perpendicular to the F, and component of F that is perpendicular to R. Vice versa, either one also can. That is the tau. And I give you an example. Just now I finished the Newton's second law for the rotational motion. Right now, we go to the standalone tau. Torque. Since we know that the torque is actually something like a rotational force, then let me give you one example. Inside a playing ground, let's say the pivot is here. So that you know that the pivot is here, which means that this is axis of rotation. Somebody sit here, M1, and somebody sit here, M2. And as a result, it is in equilibrium. Then, if it is in equilibrium, we can say that sigma tau equal to 0. Sigma tau is equal to 0. And we further discuss. Let me discuss, put it as R1, and this one put it as R2. And of course, there's an M2G here, there's M2 M1G here, Fn here, because there's a connection here between the pivot and also the rod, so there's a normal force. On the other hand, when people say here, there's M1G to cover it. And now, let us consider this part. So, for this one, there are three forces that apply on the board. On the other hand, there is no force or no net force applied on the board, and there's no net torque applied on the board. If there's no net torque applied on the board, we can put it like this, and then based on what we learned just now, we say that torque counterclockwise we put positive, torque clockwise we put negative, equal to 0. Then we can consider, as mentioned just now, torque is just a force times the displacement that is perpendicular, which is this one. And if you see that this one basically it make a turn like this. Due to the M2, it make a turn like this, which is counterclockwise, so it's which is clockwise, sorry. So there is a minus m2g r2. On the other hand, this person, he sit here and he make a turn such a way. Due to the force, the turn is like a counterclockwise direction, has a counterclockwise direction, whereby, which means that it belongs to the top counterclockwise. That is m1g r1 plus equal to 0. The next thing that you need to do is a sigma f equal to 0, where, because just now I said that it is in equilibrium. So sigma f equal to 0, which means fm minus m1g minus m2g equal to 0. Bear in mind, right now our target is to find out the torque and the force applied on the board. Not the human being, not the people, not the guys, not the girls. Let me give you another example on this one in order to find out so the torque. Let's say there's a ladder here. This is a window, smooth window. And this is the surface which is not smooth, which means that there is a friction. Surface of the ground. So this is ladder. Then in order to analyze this question, if they say it's a uniform ladder, you can consider the center of gravity is here, and this is mg. On the other hand, since there is a friction at here, you can consider there's a FF out here. So that for this question, the next thing is there any force at here? Yes, there is normal force. Fn. But is there any frictional force? No, because it is smooth. It has a smooth surface, and there's a Fn. Let me put it Fnx, and this is Fnw. Okay. So in total, there are 1, 2, 3, 4. 4 forces applied on this one, and let's say it is in equilibrium. When it is in equilibrium, you can consider that sigma tau equal to 0 and sigma f equal to 0. Let me move to the sigma tau equal to 0. Again, plus tau counterclockwise minus tau clockwise equals 0. Then, the first thing is to choose the axis of rotation. When there's an axis of something like this, because this is smooth, which means that by right, it has a chance to move down or move out. And logically, you should know that when you put a ladder like such a way, it intends to move down like this, which means this one move down, this one move to the left. So the normal frictional force is to the right, against the movement. Logical thinking, and hence this should be chosen as an axis of rotation. This point should be chosen as an axis of rotation. Axis of rotation. And if we choose the axis of rotation, then we can say that we need to find out. Maybe I use another color. What is the R1 at here, and what is the R2 at here? And also, maybe here is R3. We need to consider one by one if there is any important or not, whether it is important or not. First, all those forces applied on the axis of rotation can never contribute to the tau in this system. So that one you can directly ignore. That means that as a result, there are only two forces that contribute to the tau. I would like to repeat again. All those forces that acted on the axis of rotation, you may ignore it directly when you calculate the tau or torque. So for this case, counterclockwise, which means this one, and that means Fnw R3 minus mg R1. Fnw is horizontal force to the left. Then you need to find out the displacement that is perpendicular to the force, and it can reach the position of the axis of rotation. So you can imagine that you can calculate the R3. Then from that equal to 0. Then you can find out what is the Fn. If the Fn in this case is negative. If mostly you can think that the window will be broken. You can imagine such a way. Okay? Which means that if the mass of the ladder is too large, too heavy, this one a very large value, as a result the Fm become a negative value, then the window might be broken. And that is a way we use a mathematics or physics to prove that we cannot have a too heavy things when you hang some work. The next I would like to discuss is on the conservation of energy. And conservation of energy basically is more or less just the same, where you can use a delta PE plus delta KE equal to 0 for the ideal case, whereas the delta KE here maybe it consists of delta KET plus delta KE out. The delta KE out, which means that, let's say, just an example just now, for this case, you can imagine that delta PE plus delta KET plus delta KE out equals 0. And delta KE out is actually contributed by the cylinder, so it's actually half I cylinder omega final square minus omega naught square equal to 0 here. And here is half, is contributed by the mass here, so it's m block v square minus u square plus, and the last is plus here, mghf minus hi. And all this one, before this we cover already, so right now I will just give you a simply give you a briefing only. The most important is this one, and you should know that how to calculate all the energy by doing the tutorial. And one more thing I would like to introduce is the I. I, moment of inertia, basically is something like a, is analog to the so-called angular mass. Of course, that one is an improper term, but the proper term is moment of inertia. But basically, it's something like an angular mass, and the common thing that we use is the cylinder, and whereas the cylinder has a value of half m_r squared. Please check all those lecture notes how to get different, how to get, and also what is the value of I, or what is the formula of I when you are given a certain object. Like if a cylinder, if it rotate like this, or if it rotate like this, or if rotate like this, 3 different cases give you 3 different I. You need to consider. And for the exam, normally we will give you this one. If they say I give you a sphere or rectangular or block or cube, I will tell you what is the corresponding or what is the equivalent I for that particular object. The last thing is the rotational or angular momentum. Maybe we put it as L. Angular momentum, and basically angular momentum is something like RP also, which is mvr. You can see that all the time if I compare to the rotational and also the linear, there is a certain formula and there is a certain analogy passed. Let's say P equal to mv, so on the other hand L equal to I omega, and let's say if it conservation of energy is applicable for the linear motion, that means conservation of momentum also applicable for the rotational motion. Hence, LF equal to Li. And more or less, all those working steps is same as the linear motion. So with that, I cover this one, the rotational motion, and thank you.